What has this fish and world-famous CSIRO scientist Alan Walsh got in common? Well, the answer is both spent their working life in Australia. Walsh went on to receive a knighthood and great scientific notoriety for his work in developing this instrument, the atomic absorption spectrophotometer, which was conceived in a flash of inspiration in a Melbourne vegetable garden on a Sunday morning in March 1952. The fish went on to star in this video and also became the second course at a fish and chip shop in Ultimo on a Sunday night in March 2007. Have you ever wondered how the spectacular colours of a fireworks display are generated, or how neon signs have such vivid colours? Well, it's all to do with some simple atomic physics. When chemical elements are exposed to high temperatures or voltages, they give off coloured light. When this light is passed through a prism, it appears as a series of bright coloured lines called a band spectrum, which indicates that light is only being emitted at specific wavelengths or colours. Each chemical element has its own set of colours related to its electron energy levels, and this is as individual as a fingerprint. Alan Walsh was able to use these unique properties of elements to develop the atomic absorption spectrophotometer, often abbreviated to AAS, a tool that revolutionised quantitative chemical analysis, providing, in Walsh's own words, a quick, easy, accurate and highly sensitive method for determining the concentrations of over 65 chemical elements, in the process rendering obsolete a raft of slow and sometimes dangerous wet chemical methods. One example of this is the determination of gold in metals, where the wet chemical method took 1 month to complete. The analysis performed on the AAS takes 10 minutes. AAS analysis has found many important applications all around the world, in areas as diverse as medicine and biochemistry, food analysis, environmental analysis, metallurgy and mineral exploration, and has been described as one of the most significant advances in chemical analysis during the 20th century. The technique is mostly confined to metals, although there are a few exceptions such as silicon, arsenic and germanium. But it's not just the diversity of materials that can be analysed that makes AAS such an important analytical technique. The detection limits and precision of analysis are also outstanding. AAS can routinely perform analysis at the parts per million level, or milligrams per kilogram, and detect extremely minute concentrations of materials, such as the levels of lead in this fish. This can be done with accuracies in the 1 to 3% range. The AAS has 5 main components: the hollow cathode lamp, the burner, the monochromator, the detector and the readout. The hollow cathode lamp is the key to the success of this technique, and it's the only component that's not shared with other analytical techniques. Each element requires its own personal HCl, a device that generates wavelengths specific for that element. It means we have to have many hollow cathode lamps. It also means we can only analyse one element at a time with AAS. These days that's seen as somewhat of a limitation. Some research instruments replace the HCl with lasers. This makes them more sensitive and also allows them to analyse more than one element at a time. You can think of the flame as the sample holder in AAS. It contains the vaporised solution where the gaseous atoms we're trying to analyse absorb light from the hollow cathode lamp. Notice that it's very wide. This allows a lot of sample atoms to contact the beam to increase the total absorbance, making the instrument more sensitive. A small amount of sample is sprayed into the burner, which uses either air acetylene or nitrous oxide acetylene to generate a very hot flame of between 2100 and 2800 degrees. This releases the metal atoms from their chemical compounds and turns the sample into a vapour. The monochromator ensures that light of only the same wavelength as a hollow cathode lamp gets into the detector. We need this as other elements in the flame will also emit light at different wavelengths when in the burner. This can cause false high readings when they arrive at the detector. The detector records the amount of light emerging from the flame. If we increase the amount of atoms we're analysing in the flame, the amount of light arriving at the detector will decrease and the absorption value will increase. The more of the analyte we have, the greater the absorbance value. In order to perform an analysis with AAS, we need to complete a few simple steps. We'll use the analysis of lead in this fish as an example. The first step in the process is to get the fish into a form that can be analysed. AAS only analyses liquids. Solids and gases must first be turned into a liquid before we can perform any sort of analysis. Once we have our sample ready, we need to prepare a calibration graph. This is done by preparing a set of accurately made solutions, then recording their values on the atomic absorption spectrophotometer. You can participate by preparing your own calibration graph.
First need to zero the instrument with a blank, which is simply dilute acid. Okay, we're now ready to move on to the first standard, which is 5 milligrams per litre. Invert that to make sure it is completely mixed. And we have a reading of 0.125. To the next standard, the 10. A reading of 0.21 and 15 milligrams per litre. Reading this time of 0.32 and our highest concentration standard at 20 milligrams per litre. Giving us a reading of 0.42.
Next, we plot the absorbance values of the calibration standards on the y-axis and their corresponding concentrations on the x-axis. We can then use the calibration graph to work out the concentration of our unknown in our sample. In this instance, we take the absorbance value of the sample, come across to the graph, and then move to the x-axis, where we read off the concentration. See if you can work out the concentration of the solution that Brian's working on.
This is our dissolved up sample prepared fish, now in solution, giving a reading of 0.27. And after we've finished all the solutions, we need to clean out the internals of the instrument by flushing it with some more dilute acid.